Good morning students. Welcome to the video lecturing on groups. Today let us study on the theorems or properties on cosets. Let us take theorem number 23. If H is a subgroup of G, then there exists a one-to-one correspondence between any two right cosets or left cosets of H in G. So one-to-one means it is one-to-one means 1-1 and onto. You know 1-1 means if the elements are equal, then the images are also equal, and onto means if all the elements are the images of a set, then we can say that it is a onto function. If any function satisfies both 1-1 and onto, then we can say that it is a 1-1 and 1-to-1 function. Let us take here, let HA and HB be two right cosets of H in G. So if HA is equals to HB, then the theorem is obvious. So means there is nothing to prove here. Let HA intersection HB is equals to 5 means they don't have any common element. There is no any element which is common in both H and HB. Then define a function f from HA to HB by f of HA is equals to HB. So function means what you have to define here is, suppose we have a domain and codomain here. This is a function f. So what is defined here, what we have taken here as here, the elements of this domain, this is, we can call this one as a domain and this one is codomain. So means here the elements are in the form of HA. So H is the subgroup. So elements are in the form of here small HA, H1A, H2A, etc. it is. And here the elements are in the form of HB. H is subgroup again. The elements are in the form of here H1B, H2B, etc. it is like this. So like this you have to define a function such that what if you define a function is here f of HA is equals to HB means this element is associated with some element of this set, second set here HB. This is HA and this is HB. So this is for all H belongs to H. Now let us consider f of H1A. Just now I told you here the f of H1A is equals to f of H2A means the images of H1A and H2A are equal. Means f of H1A is same as f of H2A if they are associated with the same element. So then this implies here, according to the function what we have defined here is f of HA is equals to HB means HA is associated with HB. So this implies here H1A is equals to H2B. So here by right cancellation law on both sides, right side element on both sides will get cancelled. This is equals to, this implies here H1 is equals to H2. So we know here the definition of 1-1 function. So definition of 1-1 means this you have studied in your previous class. So 1-1 means here what here? 1-1 function. 1-1 function means if f of A is equals to f of B, then this implies here A is equals to B. If the images are equal, then the elements are also equal. I told you here f of A is equals to f of means f of A and f of B are the images of A and B under the function defined by f. So it is again same as like this only here. Suppose we have two sets, this is set A and this is set A and set B defined under a mapping f. So f of, suppose here we have A and B are some elements. So here we have f of A, f of B like this. So if f of A is same as f of B, if the images, we can call these two as images and these are the elements. If images are equal, then the elements are also equal. Then we can call such functions as 1-1. So here the images are H1B is equals to H2B. Then this implies their elements H1 is equals to H2. So here, so f is here 1-1. Further, for all HB belongs to HB. This implies here H belongs to H here. Again by this H's get cancelled. This implies here there exists HA belongs to HA such that f of HA is equals to HB. So that is every element of the codomain So here this is codomain. I told you here f of HA means the images. Images are nothing but codomain. So that is every element of codomain HB is F image of some element of the domain HA. Therefore here F is onto. Hence F is 1 1 and onto. So we can call it as 1 to 1 correspondence between two cosets of H in G. This onto means what? So onto means here if all the elements are the images here. Suppose we have two sets here. This is set A and set B and they are defined under some mapping F. Suppose it has three elements and it has here 3 to 4 element here. Suppose we have D also. Otherwise only 3 elements. Let us take only 3 elements A, B, C, and here we have 1, 2 only here. So here if A is associated with 1, B is associated with 2 and C is also associated with 3. Here all the elements, it has only 2 elements now, all the elements of set B are images. Then such functions are call it as onto function. Means if all the elements are the images of some element of set A, then we can call this one as onto function. So here it is onto. Therefore, if it satisfies both 1 1 and onto, then we can call it as a 1 to 1 function. Let us take one more theorem. If H is a subgroup of G, then all the cosets of H have the same number of elements and every element of G is in some right coset of H. So first you should read this statement once again. If H is a subgroup of G, then all the cosets of H have the same number of elements. Means all the cosets of H, whether it is right or left cosets, then they have the same elements and every element of G is in some right coset of H. So let us take here by the above theorem. In the previous theorem what you have studied here, if there exists a 1 to 1 correspondence between any two right cosets of H and G. This is studied in the previous theorem, that is theorem number 23. And this implies number of elements in any two right cosets is same. So now let A be in any element of G. We know here E is an element of H because H is a subgroup, means there should be an entity element. So E belongs to H. So this implies here A. We can take A as A into E because we know E into A is again A only, which belongs to HA, because here from the definition this is the right coset. From the definition of right coset we know here HA is equals to, this is the definition of a right coset. HA is equals to small ha such that here this H belongs to H and A belongs to G. So again here this the element of HA are in the form of small ha into H, where all H belongs to H and A belongs to G. So here it is in the form of EA. EA means it is in the form of HA. It belongs to HA because here E belongs to H and A is again same here. So because here H is a subgroup, therefore it is in this form here. So this implies here we know A belongs to HA because E belongs to H. So hence every element of G is in some right coset of H in G. So we know here this A is an element of G. Therefore it belongs to HA means every element of G is in some right coset. This is a right coset in some right coset of H in G. This is the proof of this theorem. Let us take one definition, concurrent modulo. Let H we have studied this definition in integers also. Concurrent A is concurrent to B mod M, this we studied. So let us take this definition in groups. Let H be a subgroup of G if the element A of G belongs to the right coset of HB. Just now we have studied here, if A belongs to HA means every element of G is in the right coset. So here belongs to the right coset of HB. That is, if A belongs to HB, A is an element of G and it belongs to right coset. Whether it is B or A doesn't matter here. So it should be a right coset. So if A belongs to HB, then this implies, let us operating B inverse on both sides. A B inverse belongs to H, B into B inverse. This implies here AB inverse belongs to H, B into B inverse is E, and we know H into E is H. So this implies here AB inverse belongs to H. That is, if AB inverse belongs to H, then it is said that A is concurrent to B mod H, and it is written as here A is concurrent to B mod H if and only if AB inverse belongs to H. So for all A comma B belongs to H, this is the definition of a concurrent modulo, or A is concurrent to B mod H. So means here if A is concurrent to B mod H, then AB inverse belongs to H, and conversely also we can take here if AB inverse belongs to H, then A is concurrent to B mod H. This is the definition of a concurrent modulo H, where H is a subgroup of G and A and B are elements. Let us take one more theorem, Lagrange's theorem. This theorem is important. So let us take the statement. The order of every subgroup of a finite group is the divisor of order of the group. That is, let G be a finite group and H be any subgroup of G, then order of H divides order of G. If H is a subgroup of G, then order of H divides order of G. This is the statement of a Lagrange's theorem. So this theorem may also ask for 2 marks, only the statement, and if it is a proof is asked, then it is for 6 marks. Let us take proof. Let order of H is equals to M and order of G is equals to N. So what we have here? Here G is a group and H is a subgroup. You know, subgroup means here, this implies here H is contained in G. Means H is the subset of G here. Subgroup means it is a subset of G. So let us take here, subset means it contains some elements H is contained or equal to it is. So let us take here, let order of H is equals to M and order of G is equals to N. Since H is a subgroup of G, then we know that here order of H is less than or equals to order of G. I told you here H is a subset of G, means G contains all the elements of H. So or G is equals to H also is subset. This implies here order of H is less than or equals to order of G. That is, M is less than or equals to N. So now there are 2 cases arises here. First case is when G is equals to H. We know here this subset is equal to the same set G only. So here N is equals to M. This we know because order of G is N and order of H is M. So therefore they are equal. Then the result is proved here because we want to prove this one only. No, here if G is equals to M, then order of H divides order of N, means N divides M. So there is nothing to prove here. This is only the result. And case 2, when G is not equals to H. Then G is not equals to H means there exists some element A belongs to G such that A is not in H, means there exists at least one extra element in G which is not in H. Not equal means. So since order of H is, we have taken here as M. Order of H is M we have taken here, and this implies here H has M different elements. Let us take here H1, H2 etc. up to Hm which belongs to H. They are all different. Take this one as equation number 1. All they are different. Now consider a new set. New set as H1A, H2A etc. Hma. Take this one as equation number 2. Since A belongs to G and Hi is also belongs to G. So in previous theorem we have proved this one here. If A belongs to G, then Hi is also belongs to G. So this implies here each Hi A belongs to G and all of them are different because here Hi is not equal to Hj. Here we have taken they are all different. So further all the elements of equation 1 are different from those of equation 2. Therefore we can say that if G is the union of equation 1 and 2, then we have order of H is equals to M and order of G is equals to 2M. How it is order of G is equals to M means here G is the union of equation 1 and 2. So equation 1 contains M elements and equation 2 contains M elements. Therefore sum of these two elements is 2M. So this implies here according to this definition what we have say here, we can say that here M divides 2M. So this implies we know here M divides 2M definitely. So it is here M divides 2M means here it is like this here. This is 5 divides This is 5 divides 2 into 5. That is 5 divides 10, like this it is. So this implies here m is what here? M is order of h and 2m is order of g. This implies here order of h divides order of g. So again, if g is not exhausted, means g has some more elements. There will be some b belongs to g which is neither in equation 1 or in equation 2, means g has some more elements than h. So we get a new list here, h1b, h2b, etc., hm, b. Take this one as equation number 3. Since again hi belongs to h, we know this, and this implies hi is also belongs to g, because here h is the subset of g and b belongs to g, then each hi b is also belongs to g. This is every right coset in, this is the right coset which belongs to g, and all the elements of equation 3 are different again, because here so it contains some different elements. Further, elements of equation 3 are different from those of equation 1 and 2. Now again g is exhausted. So then we can take this one as here order of g is equals to 3m, means it is union of equations. This is the union of equation 1, 2 and 3. Equation 1 contains m elements, 2 contains m and 3 also contains m elements. So therefore here this is order of this g is equals to 3m. So clearly m divides 3m. This implies here order of h divides order of g, because here order of this g is equals to 3m. No? So we know again same thing here. This is 2 divides here 3 into 2. No? That is 2 divides 6. This is correct. Therefore we can say that here m also divides 3m. So m is nothing but order of h and 3m is nothing but order of g. This implies here order of h divides order of g. So if g is not exhausted, again it contains some more elements, then we can take that here it contains, we can repeat this procedure k times. Then we have here order of g is equals to km. That is, it is the union of k equations. Order of g is equals to km, and we know that is here n divides km, because here order of g is n we have taken. Order of g is equals to n, so n divides km. Since m divides km, and this implies here m also divides m divides n. That is m is order of h and n is order of g. That is here this implies order of h divides order of g. So I hope you got this one here. Order of g is equals to kn, means here we know order of g is what here? Order of g is n we have taken generally. N is equals to km, means here n divides km we can take. So since it is, we know this m divides km, we know this definitely m divides km. Just now I told you here 2 divides 3 into 2, 2 divides k times of 2 also. So we can take here m divides km, and km is equals to, we have here km is equals to what? Km is equals to and we know here n divides km. Since n divides km, therefore we can take here m also divides n. M divides km and n divides km. So therefore we can take here m divides n. So therefore this implies here order of h divides order of g. This is the proof of this Lagrange's theorem. That is here if h is a subgroup of g, then order of h divides order of g. So this is the proof. Let us take one more theorem. Let us take first definition of a Euler's function. For all positive integers n greater than 1, then the Euler's function phi is defined as phi of n is equals to number of positive integers less than or equals to n and relatively prime to n. This is the definition of phi of n. So that is here phi of 1 is 1. So means phi of n means number of positive integers less than or equals to n and relatively prime to n. For example, here let us take phi of 8. So phi of 8 means here it is what here you have to find the positive integers less than 8 and relatively prime to 8, means first you have to find all the numbers less than 8. For example, here you have to find all the numbers less than 8 are 1, 2, 3, 4, 5, 6, 7 only. Less than or equal to 8, no, it is less than or equals to 8 we can take here. And next condition is what here? Less than or equals to n and relatively prime to n, means these two should have the common divisor as 1 and itself only. So 8 and 1 have common divisor as 1. So we can take this 1 as the 1 is the phi of 8, and 2 and 8 has the common divisor 2. So therefore this is not relatively prime to 8. 8 and 3 have only 1 and 8 as the only 1 as the common divisor. So therefore 3 is also prime to 8. And 4. So GCD of 4 and 8 is 4. Therefore 4 is not relatively prime to 8. 5 is relatively prime to 8. And 6 is also not relatively prime to 8 here, because 8 and 6 has the common divisor 2. So therefore it is not the prime number. It is not relatively prime to 8. So therefore 6 is not related to prime to 8. 7 is related to prime to 8, and 8 is not related to prime to 8. So therefore the numbers which are less than 8 and relatively prime to 8 are 1, 3, 5 and 7. So there are only 4 numbers, 1, 2, 3, 4. So phi of 8 is equals to 4. This is the definition of a Euler's function. Let us take Euler's theorem. Take a statement. If a is a positive integer and a is relatively prime to a, that is a is relatively prime to n, it is not a. So that is GCD of a and n is equals to 1. Then a to the power of phi of n is concurrent to 1 mod n. Take proof. We know that the set G of all positive integers relatively prime to n form a group under the multiplication modulo n. Let this group be G. So this group has phi of n number of elements. So that is here order of G is equals to phi of n. Hence it has n number phi of n number of elements. No, therefore we can take order of G is equals to phi of n. Let A is concurrent to A is equals to Qn plus R. This is by division algorithm. So you know here if you divide A by n, then you will get like this here. If you divide A by n, then the quotient is Q. So we can take this one as here n into Q, and the remainder is equals to A minus n Q, or A is equals to nq plus R, where R is the remainder, and this remainder should be greater than or equals to 0 and less than n. Since GCD of A and n is 1, it is given here GCD of A and n is equals to 1, then this implies here GCD of R and n is also equals to 1. So this implies here R belongs to G, because here it is defined as the elements of G are relatively prime to n. So R is also belongs to G, because here R is less than n. So then by one of the previous result, so this this we know, that is if G is a finite set, then for all I belongs to G, A to the power of phi of G is equals to E. So this implies here, what here, instead of A we have R here. R to the power of phi of n is equals to E. E is what here, identity element of G. So it is equals to, identity element of G here is 1. Take this one as equation number 1. Since A is equals to Qn plus R, this implies here A is concurrent to R mod n. We know this A is concurrent to R mod n means what here? So this means here n divides A minus R. This is the meaning of this concurrent modulo n in the real numbers. So it is A is concurrent to R mod n, means here n divides A minus R. Again if you go back the definition of divides, this implies here A minus R is equals to n into Q. This is nothing but here A is equals to nq plus R. So these are the definitions of concurrent and divides. Therefore this A is equals to Qn plus R can be written as here A is concurrent to R mod n. So this implies here taking the power on both sides. Again this is one of the property here. If A is concurrent to B mod m or n, anything you can take here, A to the power of n is concurrent to B to the power of n mod m. These are all the properties of concurrent. Therefore we can raising the power here phi of n on both sides. a to the power of phi of n is concurrent to r to the power of phi of n mod n. So this implies here a to the power of phi of n is concurrent to r to the power of phi of n. We know here it is equals to 1 is equals to 1 mod n. This is from equation number 1. So this is only our proof. So that is here a is concurrent to a to the power of phi of n is concurrent to 1 mod n. So where this a is a positive integer and a is related to prime to n, that is GCD of a and n is equals to 1, then a to the power of n is concurrent to 1 mod n. So this is the proof of this theorem. Last, let us take one more theorem, Fermat's theorem. If p is a prime and a is any integer, then a to the power of p is concurrent to a mod p. So take proof. There arises two cases. Case 1, if a is related to prime to p, means GCD of a and p is equals to 1. Then by Euler's theorem, just now we have proved here, if GCD of a and n is 1, then a to the power of phi of n. So this is Euler's theorem, just now we have proved here, if GCD of a and n is equals to 1, then a to the power of phi of n is concurrent to 1 mod, what we have said here, it is equals to 1 mod n. Just we have studied in previous theorem, that is previous theorem is what, there we have studied this one, a to the power of phi of n is concurrent to 1 mod n. So same thing here, if GCD of a and p is equals to 1, then by Euler's theorem we have a to the power of phi of p is concurrent to 1 mod p. So since we know, since phi of p is equals to p minus 1, because p is prime, therefore we have here phi of p. What we have seen here, definition of phi of p is what here, phi of p means it is equals to a positive integer p which is less than or equals to which is less than or equals to what here, which is less than or equals to p and related to prime to p. So therefore here here it is a and p are related to prime to 1. So therefore we can say that here phi of p is equals to p minus 1. So now a to the power of phi of p is p minus 1 is concurrent to 1 mod p. Here only you have to substitute. So this implies here multiplying a on both sides. So a to the, this is again the property of a concurrent modulo m. So this we have seen here, if a is concurrent to b mod m and c is concurrent to d mod m, then this implies here a into c is concurrent to b into d mod m. These are all you studied in our previous classes here in PUC 2, I think it is. So we can, so we can multiply here, we can multiply on both sides here. So that is here a is concurrent to this is a into a to the power of p minus 1 is concurrent to a mod p. So we can take this one as here a to the power of, add their powers here, a to the power of p minus 1 plus p is concurrent to a mod p. So this is only the proof. Let us take here case 2. If a is not related to prime to p, then see what happens. That is the GCD is not equals to 1. That is GCD of a and p is not equals to 1 and p is prime. So p is prime means here this implies here p divides a. If GCD is not equals to 1, definitely here p divides a. For example here, if GCD of 2 and 8 is not equals to 1, so what we have here, what we can see, GCD of 2 and 8 is equals to how much here, 2, this we know here. So according to this, p is a prime, means here this is p is not prime, no, it is, we can take here 8 and 2 we can take here. Since p is prime, this is in the form of a and p, here this is a and this is p, and p is prime. So this implies here what, p is prime, this implies definitely p divides a, this is a and this is p. So definitely this 2 divides 8, this we know here. So this implies here p divides a means, we know again definition of divides. Definition of divides is what here, if a divides b, then this implies here, this is we can take this one as if a divides b, then b is equals to n into q we can take, n into a we can take here. So or we can take here b is equals to n into a, no? So it is also same here. B is equals to n into a means we can take this one as here. We can take, otherwise we can take directly also here. If a divides b, then b is concurrent to or it is like this here. If a divides b minus m, then this implies here m is concurrent to here. This is b minus m is equals to n into q, or it is we can take here this is we can take this one as here b minus m, no? So it is b is concurrent to m mod m it is. So this implies if p divides a, then this implies here a is concurrent to 0 mod p. So raising the power p on both sides, a to the power of p is concurrent to 0 to the power of p mod p. So 0 to the power of p means 0 only, it is mod p. Take this one as equation number 1. Since here p divides a we know, then this implies p also divides minus a. So means here 5 divides 10, so 5 also divides minus 10. Don't see the quotient whether it divides or not. We should divide it exactly. So this implies here, this implies what here, a is concurrent to 0 mod p and 0 is concurrent to a mod p. So a is concurrent to 0 mod p means p divides a minus 0 it is. This implies here, this means here p divides a minus 0, and this implies here p divides 0 minus a. This is the definition of concurrence modulo. So p divides 0 minus a means p divides minus a, this one, and p divides a minus 0 means p divides a. So from equations, this is second equation, and here we have first equation. From these two equations we can take this one as here a to the power of p. A to the power of p is concurrent to a mod p. So this is only the proof. So this is, we can call it as a Fermat's theorem.